Does it mean that when we double the insulation thickness, we would have reduced the heat transfer by half? How thick should the insulation be? Before we look into the diminishing effect of insulation thickness, we need to understand the key concept behind heat transfer. Heat transfer is given by Q equal to UAT, where Q is the heat transfer in watt, U is the heat transfer coefficient in watt per meter squared Kelvin, A is the area in meter squared, T is the temperature difference in Kelvin. And we know that U is inverse to R, where R is the thermal resistance in meter squared Kelvin per watt. Therefore, Q equal to area times temperature difference divided by R value, and R value is a function of thickness, which R value equal to L divided by lambda, where L is the thickness of the material in meters and lambda is the thermal conductivity in watt per meter Kelvin. Using hypothetical figures, say for an area equal to 100 meters squared and temperature difference being 15 Kelvin, using the heat transfer formula, we are able to calculate heat transfer at different R value as tabulated in the table. This example illustrated, when we add 0.4 meter squared Kelvin per watt of insulation, we will reduce the heat transfer by about 80% from the original. By doubling the R value to 1.0 meter squared Kelvin per watt, the heat transferred is reduced to 90%, i.e. a 10% increase from previous. Further increasing the R value to 1.5 meter squared Kelvin per watt, the heat transferred is 93.3% less than the original. There is a very big drop-off in heat transfer reduction as R value increases, to the extent it is not viable to add thickness for the little saving you get. The graph showed the diminishing effect of insulation thickness. Insulation thickness with R value above 4 meter squared Kelvin per watt gives very little additional return on your investment, more so for duct insulation at R3. I don't see the R value stated in the BCA/NCC be increased in the near future.